Today I will be presenting the third in a multi-part series of webinars addressing aerospace fuel system modeling with Flowmaster. I'm going to start today's presentation with a brief overview of the benefits of using one-dimensional CFD software in the engineering process. We will then look at a review of the one-dimensional fuel system model for a typical two-engine passenger aircraft we used in the last two sessions. After the overview, we'll look at adding detail to the tank model using the Flowmaster Advanced Tank component. We will then perform two case studies related to the advanced tank, a venting scenario and a fuel tank inerting scenario. After the case studies, we'll discuss the next topic in this series and have a question and answer session. Risk is always a concern for companies, and usually, as a project progresses, the risks associated with the project tend to decrease. One of the main driving factors behind this is the increase in information that naturally happens as a project matures. By gaining knowledge very early in the process, designers and engineers can lower that risk even sooner. This is where upfront simulation can add significant value to the process. By allowing engineers and designers to investigate a growing number of prototypes virtually before any physical models are constructed, investment in upfront CFD can have significant value by lowering physical testing efforts later in the design. Because physical testing is time-consuming and expensive, virtual prototyping allows more variants to be examined in a shorter amount of time. Flowmaster fits into this idea because it is a one-dimensional computational fluid dynamics simulation tool that allows engineers to simulate complex thermofluid problems at a system level so that they can understand aspects of the design such as pressure, temperature, and flow rate throughout that design. Access to performance data early in the design process is always a challenge, but Flowmaster supplies built-in data from DS Miller out of the box to give you a baseline to work from. You can investigate both steady-state and transient behavior in your system, and you have the ability to simulate different types of fluids, including liquids, gases, refrigerants, and steam. There are a host of specialty solvers for both complex phenomena like swirl and priming, or for making potentially repetitive tasks simple, such as performing a flow balancing analysis. Flowmaster has been helping its users meet these requirements for over 25 years across many industries throughout the world, including our focus today, the aerospace industry. Before we look at today's studies, let's take a few minutes to review what we did last time and expand on the basic model with the addition of the advanced tank component. Here is the schematic representation of the simplified passenger aircraft fuel system that we built and used in previous presentations. The three large blue sections represent the wing and the center fuel tanks. The white boxes represent pumps, and the fuel feed and transfer plumbing is represented in green. Refueling lines are represented in dark blue. Shut-off valves are depicted throughout the model as the circular symbols indicating normally open or normally closed. And here is a Flowmaster system model drawn directly on top of the schematic image. It includes source components for our boundary conditions and extra loss components for items like filters and couplings. Again, the tanks do not take up the whole area outlined in light blue, but instead are single discrete components. The thin link lines represent a direct connection between adjacent components and are not pipes themselves. Nodes sit in the middle of the links and serve as convenient points to enter elevation data and interrogate flow results of temperature and total pressure. We took a more detailed look at the arrangement of the pipes, pumps, valves, and tanks in the first two presentations. For a more thorough explanation of the base model, you can re-watch those earlier presentations. For today's study, we're going to focus specifically on the wing tank system in detail. To add fidelity to the tank simulation in our system model, we've replaced our simple tank models consisting of a single Flowmaster reservoir component at each location and replaced it with a system of two advanced tank components. We've used separate tanks to try and capture the effects of having separate tank cells within the same overall assembly. We can use the multiple arm connections on the advanced tank to model the effect of having multiple connections between each cell, such as the holes through a wing rib. With the advanced tank component, we can position each connection point at a different elevation and with a unique size and amount of pressure restriction. Let's take a closer look at the left wing tanks to learn a bit more about the advanced tank. Here's a detailed view of the left wing tank assembly in the aircraft model. The assembly is a combination of two new advanced tank components, an inner tank cell and an outer tank cell. All of the flow into the tank from the refueling gallery comes into the inner tank. Similarly, the pumps that supply the engine and crossfeed gallery draw from the inner tank only. The outer tank behaves like an overflow volume. It starts to fill when the inner tank nears its capacity and gravity feeds back into the inner tank as that tank empties. In our model, the two tanks are connected via 5 separate connection points, or arms. Each arm can have a unique value of elevation and pressure loss. We're using the 12-arm tank component, though we're only using some of the connections. More connections could be used if we desired, and any unused connections are assumed sealed shut. The advanced tank also gives us the ability to model a compressible gas vent as part of a larger compressible flow circuit. Here, we've added a simple vent model, modeled as an orifice plate and a pressure boundary condition, but a more elaborate system with plumbing and valves is also possible. The advanced tank component contains several signal connections to allow a level of control similar to what was demonstrated in the last session. Using the tools in the Aerospace module, or with the addition of some simple controllers, we can change the pressure and temperature at each boundary condition as a function of altitude to apply a flight profile, something we explored in the previous presentation. Because we're relying on the advanced tank component so heavily for our analysis today, let's spend a little more time learning about it. Fundamentally, the difference between the advanced tank and the traditional reservoir components in Flowmaster is the ability to combine liquid and gas within the same volume. The liquid and gas interact via pressure and volume and can be used to force one another in and out of the tank based on the pressure and flow conditions at the arms. There are separate dedicated connection points for the gas space and the liquid space. Liquid will not overflow through the vent, and gas will not leave through the liquid connections. The gas connections take the form of 2 compressible arms at the top of the tank volume, and either 2, 3, 10, or 49 liquid arms are available depending on the specific advanced tank component that you use. Also, unlike traditional Flowmaster components, it is possible to leave unused arms disconnected. The signal connections on the advanced tank allow for control over the temperature of the tank contents, the pressure in the tank, the heat flow rate through the walls, and a changeable base elevation. The heat transfer coefficients for heat loss or gain through the walls for the liquid and the gas can be set separately, and an internal vent model is also included that can override or supplement the gas connections in a similar way to how the standard reservoir components operate. Because the component is more complex, the data entry requirements are somewhat more demanding for the advanced tank. With up to 52 total arms, a compact way to define the position, size, and loss characteristics of each arm is needed. A data table is a simple way to do this and is easily accessible. Characteristics of the overall geometry and position of the tank are included, like height, cross-sectional area, and base level. You can also define a custom relationship between either area or tank volume as a function of height to account for complex tank shapes. We'll use this capability in our example models today. Heat transfer, compressible flow, and gas concentration data are available for more complex analyses, and we'll explore the latter in our Inerting case study. One powerful capability that all the advanced tanks and many of the standard reservoir models have is the ability to set a custom relationship between elevation and either cross-sectional area or volume. In this way, it is possible to accurately model the fluid head effects in tanks with a non-uniform cross-sectional area. Using geometry and calculus, or in our example, 3D CAD software, we can generate a relationship of tank volume or area as a function of liquid level for our inner and outer wing tanks and update that relationship as the initial physical design progresses. In our case, we can use the capability to accurately model the shape of 2 non-rectangular tanks that have a non-uniform cross-sectional area due to their location inside of an aircraft wing with a 5-degree dihedral. Because of the angle of the tanks, the volume increase as a function of height has a pronounced S-shape, instead of the linear relationship expected from a constant cross-section tank in a level attitude. With the modifications and additions to the model complete, let's look at the first case study, an analysis of the vent system performance during both refueling and aircraft maneuvering. When a fuel tank is empty, the entire volume is occupied with gas. This gas must be displaced during the refueling process, so vents must be included in the design for the gas to escape with minimal restriction. In addition to refueling, when an aircraft rapidly climbs or descends, the atmospheric pressure outside of the aircraft may change more rapidly than the vents can keep up with. The U.S. Federal Air Regulations, or FARs, dictate that the capacity of the vent system must allow for the rapid relief of pressure, and if there are interconnected tanks, which we happen to have in our system, their vent systems must also be interconnected. Aircraft tanks are designed with weight as a primary constraint and are not always capable of withstanding large internal or external pressure differentials, so it's important to minimize the difference. There's an optimum size and number of vents to satisfy these conditions while minimizing weight, cost, and complexity, and we can use 1D analysis to help refine our design towards this optimum condition. In this case study, the first scenario we will explore is that of ground refueling. We will start with our simplified vent system and model it as a group of single sharp-edged orifice plates that represent the total vent restriction in each flow path. One orifice is attached to one side of each tank cell. The orifices each assume a 2-inch pipe size and a 1-inch orifice restriction. The fuel tanks are interconnected, both with a shared gas connection at the top of the tank and 4 liquid connections between them. The loss associated with each connection is set to a nominal value at this point in the design process, but could be adjusted as information such as the size and number of holes and their restriction caused by maybe additional baffling between tank cells is refined. Boundary conditions attached to the downstream arms of the orifice plates are set to a standard day sea level condition of 14.7 psi and 59 degrees Fahrenheit. Lastly, a refueling rate of 250 gallons per minute used in the previous refueling studies is also assumed. After running a transient simulation spanning the refueling process from completely empty to completely full tanks, we can first look at a combined plot of fuel mass and refueling flow rate versus time. Here you can see the constant addition of fuel leads to a linear increase in mass in the inner tank until it fills sufficiently to begin to spill into the outer tank. As the outer tank becomes full, the inner tank and vent system fills to completion and the refueling flow shuts off. Here's a plot of liquid level versus time. Here you can see the effect of our nonlinear relationship between volume and tank liquid level due to the angle and shape of the tanks. Lastly, we can look at a plot of the pressure drop across the orifice component, which should equal the pressure differential between the interior of the fuel tanks and the ambient atmosphere. With a 1-inch vent connected to each tank, the difference in pressure is around 3/100ths of a psi, which is well within the limitations of our structure. With no real refinement needed for this case, let's move on to a more limiting one. Emergency climb and descent. Most commercial jet aircraft at typical loads are capable of sustained rates of climb of around 2,000 feet per minute. We're simulating a worst-case scenario of a very rapid rate of climb of 5,000 feet per minute and a maximum performance descent of 10,000 feet per minute. We want to understand what pressure differential we'll see across our vents with these rapid changes in atmospheric pressure. We performed a series of analyses at several orifice sizes to determine if smaller vents were acceptable. We performed the analysis with a minimal amount of fuel to maximize the gas volume that must be evacuated and returned to the tank during the climb and descent maneuvers. Lastly, we'll look at a case of a blocked vent where only one of the 2 vents is operating, and the second tank must vent into the adjacent tank through the interconnection between them. Here you can see the results of tank mass flow for the 1-inch orifice size study. Here you can see that despite an almost 4-fold difference in volume between the inner and outer tanks, the same sized vent means that almost the exact same mass flow rate flows through each of the two vents. You can see, based on the green line, that a significant flow of gas moved from the inner tank to the smaller outer tank to leave via the outer tank vent. This is a major benefit to having interconnected tanks. The flow through the vents will equalize naturally between all of the volume in the system, regardless of individual cell size. Here is a plot of pressure as a function of time. Atmospheric pressure is plotted in black, with the three orifice sizes colored from largest to smallest in green, blue, and red. From here, it is evident that the 1-inch vent size has considerably less pressure difference during maneuvering, and the smallest half-inch orifice has a significant amount of pressure difference during the descent. At a peak of approximately 6 psi, this might be enough pressure to crush the fuel tank from the outside. Lastly, let's look at a plot of pressure drop directly. Here you can see that the half-inch orifices do indeed spike to almost 6 psi. The 3/4 inch orifice has a maximum of about 1.5 psi, which may be acceptable, and the 1-inch orifice experience about a 0.5 psi difference. Although both the 1-inch and the 3/4 inch sizes seem acceptable, let's continue our investigation and look at one more what-if scenario: blocked vents. Here, we've set the orifice size of the outer vent to a very small size, effectively blocking it, simulating the presence of ice or other foreign material. With one blocked vent, the 3/4 inch size now experiences a 4.5 psi difference during the descent, while the 1-inch size only has a 1.5 psi difference. Based on this seemingly worst-case scenario, 1-inch vent orifices seem to be the best option for our specific design, because they can tolerate complete blockage of one side of the tank system and deliver performance that protects the structure of the tanks. We can once again look at the total flow rates into and out of our tank during the climb and descent of the aircraft. Here you can see that almost all of the flow entered and left through the unblocked inner tank vent charted in blue. The smaller gas volume contained within the outer tank was able to transfer through the larger inner tank via the interconnected internal vent, charted here in green. A very small amount of flow was able to leave through the outer tank vent, which you can see on the red line as a small deviation from zero during the climb and descent. Although our vent model is simplistic, comprised of only a single orifice per tank, we showed that it is simple to perform what-if case studies and investigate the effective vent size, location, and blockage on pressure differential between the inside and outside of the tank during both liquid filling and due to pressure changes caused from rapid climb and descent. For our second case study, let's look beyond venting to an important area of focus in aircraft fuel system design over the last several years: fuel tank inerting. Inerting has become an increasingly important issue within the last decade as the FAA and aircraft manufacturers seek to eliminate the risk of explosion inside of fuel tanks. Federal air regulations now dictate that sources of combustion must be eliminated. Solutions to the problem include removing heat-generating machinery like cooling packs, pumps, and fans away from fuel tanks. A more complex and active approach to flammability is to remove the possibility of combustion entirely by displacing the oxygen and combustible fuel vapor by introducing an inert gas like nitrogen, argon, or carbon dioxide directly into the fuel tank ullage. For our example, we're going to study the effect of introducing nitrogen-enriched air into our model. We will use a component called the fluid modifier, along with a Flowmaster capability called multi-fluid simulation, to model a simple air separation module, which is sometimes called an onboard inert gas generating system, or OBIGS. The fluid modifier component passes along the pressure, flow, and temperature conditions of the input fluid, but replaces it with one or more different fluids that we can specify. In our model, we'll replace a standard air mixture with a new mixture that is much richer in nitrogen. We'll set the flow rate to 200 pounds per hour of nitrogen-enriched air mixture in line with the capability of commercially available equipment. We will simplify this demonstration by locking the mixture of nitrogen to air at 95% and 5% respectively. A more complex model could vary the mass flow rate and concentration of nitrogen as a function of air temperature, pressure, and flow rate, or any other input variable. We'll then feed the inert gas from our simulated air separation module into both tanks through a common gas connection point in the vent system. With the advanced tank component, we can set an initial gas concentration in the tank, so we'll set that to the upper flammability limit of Jet A of 5% as a worst-case condition. The remainder of the gas in the tank is set to nitrogen and oxygen in normal ambient proportions. The underlying technology behind this type of study is an analysis option in Flowmaster called multi-fluid simulation. Multi-fluid simulation is an option that you can enable on either compressible or incompressible analysis types and allows the real-time mixing of multiple liquids or gases in a single system at one time. These mixtures must be in the same phase, so you can mix liquids with other liquids and gases with other gases, but you cannot mix a liquid with a gas to model a multi-phase phenomenon. The bulk properties of the mixture are derived through a weighted average approach of the individual components of the mixture. There are some limitations. Flowmaster doesn't model buoyancy effects of mixing gases with large density differences, and also assumes perfect mixing in each individual component or segment within a pipe. The last piece of the puzzle for performing inerting studies in Flowmaster is fluid property creation. Flowmaster ships with several fluids for the aerospace industry, including liquid Jet A. But to properly model an inerting system for our case study, we also need fluid properties for Jet A vapor. Although jet fuel vaporization is a complex phenomenon and different chemical species evaporate at different rates, for our model, we'll make a simplification and assume a distribution of alkanes that mimics data available from a public source. We will then make use of Flowmaster's integration with NIST RefProp to quickly and easily create a custom vapor mixture based on fluid component and mole fraction. Flowmaster queries RefProp and generates curves and surface maps of essential fluid properties as functions of temperature and pressure to use throughout the analysis. After building the model and creating our custom fluids, we can then run a multi-fluid analysis. Once complete, we can plot results of concentration of our two combustible gases over time. The concentrations of oxygen and Jet A are relatively small compared to nitrogen, so we removed nitrogen from this chart. Here are a few key points. At 12% oxygen, the atmosphere in the ullage is below the limiting oxygen concentration, and the tank is now effectively inert. Our system, at a flow rate of 200 pounds per hour of nitrogen-enriched air, takes 140 seconds to inert the smaller outer tank, and about 530 seconds to inert the larger inner wing tank. The wings can also be inerted by bringing the concentration of jet fuel vapor below the lower flammability limit of 0.7% for Jet A. It takes just over 300 seconds to do this in the outer tank cell, and about 1,400 seconds to fully inert the inner wing tank. It's important to state that these limits apply at sea level conditions and are impacted by changing temperature and pressure, an issue we did not address in this study. These are details that could be included in a more complex Flowmaster analysis, but we omitted them here for demonstration and simplicity purposes. Using multi-fluid simulation, along with the advanced tank component, we can now use Flowmaster to study inerting scenarios and ensure that our tank, vent, and inert gas generation systems are all properly sized and configured, helping to find a solution to a very serious aviation safety issue. Today we looked at how advanced tanks can bring new capability to your fuel and vent system models by allowing you to combine the liquid fuel circuit with the compressible gas circuit in a single model. The addition of a complete venting system to a fuel system model adds a general level of fidelity, but also gives you the ability to look at new scenarios. Important issues like tank venting under conditions of stress like rapid descent and fuel tank inerting can now be studied with simple 1D system level analysis, which lets you work quickly and easily, trying many configurations and scenarios in a short amount of time. For the final presentation in this series, we will add one more enhancement to our fuel system model, the addition of ejector or jet-style scavenge pumps to our fuel tanks. These types of pumps serve two purposes in aircraft fuel systems. The first use is to continuously remove any water contamination from the tank that may have collected in the sump, and also to scavenge the last remaining fuel out of an auxiliary tank like the center tank in our design. Ejector pumps can require a significant amount of performance data to run properly in Flowmaster. So we'll use a new capability of Flowmaster and our 3D CFD tool, FlowEFD, to quickly and easily characterize the performance of the pump using CAD-embedded 3D computational fluid dynamics, and transfer that information automatically to Flowmaster for further 1D analysis.